Module 4. MEMS Data Capture and Analysis. In this module, we will use the Nucleo F401RE and the X-Nucleo IKS4A1 expansion board, in addition to MEMS Studio, to capture real-time data from the LIS2DUX S12 accelerometer. We will then analyze the captured data, labeling specific motion states for use in the next module. Finally, we will examine the labeled data to determine any features of interest. The LIS2DUX S12 is an ultra-low power, 3-axis smart digital accelerometer with advanced features such as QVAR electric charge variation detection and a machine learning core. It is capable of sampling data at up to 16 Gs of full scale, with supported output data rates from 1.6 Hz to 800 Hz. MEMS Studio can monitor real-time sensor data and log this data to a file. We will be capturing acceleration data from the sensor in 3 states. Stable, where the board will rest on the table. Movement, where the board will be gently moving in your hand. And shaking, where the board will be vigorously shaken. The captured data will be analyzed in the time domain and the frequency domain in this module. This same data will be used to train a machine learning model in the next module. If you have closed MEMS Studio after the previous module, double-click the icon to reopen the application. In the Connect sidebar menu item, ensure that the communication type is set to serial. The communication port should be automatically selected by the tool. Click Connect to establish the initial connection to your board. The GUI will show the default expected sensors for your board configuration. For this module, we will select the LIS2DUX S12 accelerometer to replace the LSM6DSV16X accelerometer as the source of acceleration data. Click on the drop-down menu for the accelerometer sensor. Scroll down if necessary and select the LIS2DUX S12. Then click the Select button at the bottom right. The screen will automatically change to the Quick Setup menu. Click the Play button at the top left of the sidebar. This will enable the sensors and start streaming the data from the board to the tool. Since we will capture simple human motion with the accelerometer, set the accelerometer full scale to 16 Gs and the accelerometer output data rate to 100 Hz. You can leave all the other options at their default values. Now, select the Save to File menu option. Click Browse at the top right. Then navigate to the C:\MEMS_Studio-Workshop folder. Then open the Module 4 folder. Then open the Logs folder. Name the file acceleration.csv. Note that if you do not select a unique file name, the tool will append any newly captured data to the end of your file. Click Save. Disable the Logging Timeout option if it is enabled. The Data subpanel displays the sensors and information sources that can be logged. You can select the sensors that you wish to log and deselect the sensors that you do not need to log. Right-click on the Data subpanel. Click Unselect All. Then make sure to select only the timestamp and accelerometer. We will not capture the data from the other sensors on the board. The Data Log Period Source option allows you to select the source of your data log periods. Since we will only capture data from the accelerometer, select this option. Now we are ready to capture sensor data. Be very careful during the motion capture not to press down on the IKS4A1 MEMS shield, as this can press the reset button, causing a board reset. First, leave the board motionless on the table. Click the Start button. We will let the tool acquire approximately 30 seconds of data. We can click on the Line Charts option to view the sensor data during this acquisition. You can click the left arrows next to the graphs of the gyroscope and magnetometer to collapse these graphs. The acquisition time is displayed at the bottom right of the application. Move the board to a different orientation and leave it motionless on the table again for approximately 30 seconds. Finally, move the board to a final different orientation and leave it motionless to capture another 30 seconds of data in the stationary position. Next, pick up the board and rock it gently in your hand. Let the tool acquire another 30 seconds of data. Then, turn the board gently along any axis and acquire another 30 seconds of data. Finally, rotate the board yet again and acquire a final 30 seconds of data during gentle motion. Now we will shake the board. Vigorously shake the board along any axis for approximately 30 seconds. Then switch the axis of your shake and continue shaking for another 30 seconds. Finally, shake the board along the final axis for a further 30 seconds. At this point, you will have captured at least 4 minutes and 30 seconds of motion data in 3 major states: stationary, movement, and shaking. Return to the Save to File option and click Stop. Then, click the Stop button in the left menu pane. We are now ready to analyze the captured data. In the left menu, select the Data Analysis tab. Click on Browse at the top right. Then navigate to the C:\MEMS_Studio-Workshop folder. Then open the Module 4 folder. Then open the Logs folder. Select your acceleration.csv file. This will open the file and display your time domain data. Select one stationary period by clicking on your graph near the beginning of the period, then clicking at the end of the period. This should show as a highlighted section. Click the Set Label button at the right side. Label this data as stable and click Confirm. Select the next stationary period by clicking at the beginning of the next period, then clicking at the end of the period. Click the Set Label button, and for the label name, select Existing Label from the drop-down menu as Stable. Perform the same action for the third stationary period. Next, we can select the gentle motion period in one block. Click on the graph right before you pick up the board. There should be a small peak in the data. Then, select approximately 90 seconds of data from that point, up until the obvious shaking period. Click the Set Label button at the right. Set the label as Movement. Click Confirm. Finally, select the shaking period by clicking near the beginning of the shaking period, shown by the quick peaks, until the end of the shaking period. This should correspond to approximately 90 seconds of data. Click the Set Label button at the right and set the label as Shaking. Click Confirm. Now click on Save Labeled Data on the right. A pop-up will ask you to set the base name. Then navigate to the C:\MEMS_Studio-Workshop folder. Then open the Module 4 folder. Then open the Processed folder. Set the base file name as Processed. This will save all the labeled data with Processed as the base and the label appended. Click on the Frequency Domain tag on the left menu bar. A pop-up may appear asking to check the sampling frequency. Click Check to verify that it is in the expected range, then click OK to continue. Two graphs will be displayed. The top graph shows the same time domain signal. The bottom graph shows the frequency domain signal. On the right are several options on how to view the signal. We shall leave them at their default values, but more details on each setting are available in the user manual for the tool. If we want to see only the labeled periods, we can select Browse at the top right and select one of our exported data files. Select one of the stable periods in the time domain signal graph, as we did in order to label the stationary period. In our graph, it shows some peaks at the low end of the frequency range, consistent with very low or no motion, with the peak mostly dominated by one axis. Now, select a gentle motion period by clicking at the beginning of the period to the middle of the movement period. The frequency domain signal will now be displayed for the movement period. Again, some peaks will be apparent at the low end of the frequency range, but this time, the peaks for all axes should be more apparent. Finally, select the shaking period in the time domain graph. There may be multiple peaks, depending on whether you changed the frequency of your shake. This peak should now be shifted to the right. The value of the peak may also be greater. Now, click on Spectrogram on the left menu bar. This will show the spectrogram of the signal. A spectrogram analysis is used to evaluate the frequency spectrum over time. This is very similar to the frequency domain analysis we just completed, except each vertical slice represents the frequencies present in the sample at that particular instant, while in the frequency domain analysis, we selected a larger period of time. When analyzing this graph, you can select regions of interest by shrinking the orange box at the bottom of the graph. In our case, we will look at the graph in its entirety. The beginning of the graph, corresponding to the stationary time period, shows a uniform distribution, with a yellow band near zero, signifying a higher signal. The higher frequencies show a lower signal, signified by a darker red or even black color. The gentle motion period should show a similar signal, except that the lower frequencies will show more orange as opposed to the darker color of the stationary period, signifying some moderate signal strength as expected by motion. Finally, for the shaking period, the yellow band, signifying a higher signal, will be shifted to a higher frequency, with orange more evenly distributed around the dominant shaking frequency. Return to the time domain graph by clicking on Time Domain on the left menu bar. From a brief inspection, we can see that we can differentiate between the different labeled periods by the peak-to-peak values within the periods. The stationary period will have extremely minimal peak-to-peak differences. When we refer to peak-to-peak differences, we are speaking of the local minima and maxima, very close together in time within the same period, not across the whole time period. The movement period will have moderate peak-to-peak differences. The shaking period will have large peak-to-peak differences. We will use this information in the next module when we generate a machine learning model in order to detect the state of the board. In this module, we use the MEMS Studio Save to File functionality to save accelerometer data to your PC. Then we use the data analysis tools to view the time domain, frequency domain, and spectrogram of the captured data, and labeled our data into different states. Finally, we examined the data in order to determine a feature of interest that we could use to generate a machine learning model. This concludes Module 4.